So in Chapter 8, Section 3, we're looking at confidence intervals for the mean, where sigma, which is your standard deviation, is unknown, and n, which is your sample size, is less than 30. So when we don't know our population standard deviation and we know our sample size is less than 30, we need to not use the standard normal curve. We're going to start looking at t-distributions instead. So we're talking about a t-distribution. There are some characteristics. Hey, that thing's in your way. Let's close that. There are some characteristics that they share with our standard normal distribution, but there's some that they're not sharing. So the characteristics of the t-distribution, the ones that are similar to the standard normal distribution, is that it's bell-shaped. It's symmetrical about the mean. You can see that here. Symmetrical about this mean. The mean, the median, and the mode are all equal to 0, and it's right in the center again. And the curve never touches the x-axis. Remember, it keeps going on and on in either direction. Now, things that are different is that our variance is going to be greater than 1. So that means our standard deviation squared is greater than 1. Also, the t-distribution is actually a family of curves based on the concept of the degrees of freedom, which we'll talk about in a moment, which is related to the sample size. As the sample size increases, the t-distribution will approach the standard normal distribution. So over here we have our degrees of freedom being 2. And you can see that this brown curve here is a little bit lower than our degrees of freedom being 5, a little bit higher here with the blue curve. And our standard normal distribution is the red curve here. You can see slowly they're going to approach that red curve, and we'll have the normal bell curve. So the degrees of freedom that we talked about is the number of values that are free to vary after a sample statistic has been computed. They tell you, the researcher, or you, which curve to use out of a family of curves. So the formula for the confidence interval is quite similar to the confidence intervals we've been calculating yesterday and the day before. But now that we don't have a standard deviation for the population and our sample size is less than 30, we can use this new formula here, where we have x bar, meaning your sample mean, subtract your t-distribution now of alpha over 2 times your sample standard deviation, S, remember, is sample standard deviation, over the square root of n, which is your square root of your sample size, which has to be less than 30. That's black, not yellow. And again, same thing on this side, except with a plus sign. Now, df here is your degrees of freedom, and your degrees of freedom that you're going to be looking up is always going to be n minus 1. So you're going to take your sample size. If your sample size is 15, your degree of freedom is going to be 15, subtract 1. So here's a picture of the t-distribution table that's found in your book. If we're looking for t of underscore alpha over 2 of 95% confidence with a sample size of 10, what we need to look up is on top, it says confidence interval, which is here. I know it's a little bit blurry. My phone doesn't take really good pictures, and I couldn't find a good one online. So we're looking for the confidence interval of 95%, which is this column here. Let me get a brighter color. So 95%. We're not paying attention to the one tail or the two tails currently. We want to come down, and we want to know what is our degrees of freedom. If our sample size is n, our degrees of freedom is equal to n subtract 1. So if we have 10, we're looking at 10 subtract 1, which is 9. So we come down our degrees of freedom column to 9, and we go over from 9 and try to make, oh, I have a straight line thing, don't I? And we make a straight line from 9. And we look down at 95%. Sorry about that. Don't know what my computer's doing. 95%, and we get 2.262, I believe that says. Yes, so we get our t alpha over 2 equal to 2.262. So we can substitute this number into the formula and calculate it just as if we were doing with the z underscore alpha over 2. So here's a problem we can use with t-distributions. If we have 10 randomly selected vehicles that were stopped and the tread depth of the right front tire was measured. The mean was 0.32 inch, and the standard deviation was 0.08 inch. Find the 95% confidence interval of the mean depth. Assume that the variable is approximately normally distributed. So we're looking at the formula we have. Let's change my color back to black. X bar, subtract t sub alpha over 2 times our standard deviation of the sample over the square root of the sample size is less than or equal to. Sorry, that's algebra we're doing less than or equal to, and sorry, let's erase this. We're looking at less than mu less than x bar plus t sub alpha over 2 of our sample standard deviation divided by the square root of n. So first thing we need to find is what is our t sub alpha over 2 going to be? So our t sub alpha over 2 is going to be, we need to find our degrees of freedom. Degrees of freedom for this one is n minus 1. So we're looking, what was our sample size? Our sample size was 10. So our degrees of freedom is going to be 9 yet again. Why does it keep doing that? We're also looking for a 95% confidence interval. So on the table we found out that the 95% confidence interval with the degrees of freedom being 9 was 2.262 if I remember correctly. 2.262. We substitute this number into the formula along with the other numbers we have. So our x bar, our mean, was 0.32. And our subtract t, so we say subtract t, which was 2.262 times our sample standard deviation, which was 0.08, divided by our sample size square root, so square root of 10. And we get, magic calculator, so we get 0.26, actually that'll round up to a 3, 0.263 is less than mu. And I'm going to calculate it again, except this time I'm going to calculate it with a plus sign between them. This becomes a plus on the second one. When we add those, we get 0.377. So we know that our mean is going to fall, 95% sure that it's going to fall between 0.263 of an inch and 0.377. Now we're looking at our inches. Our inches were measured in 2 decimal places. So I can actually round these to 2 decimal places. So I have 0.262, and I have 0.38 of an inch. As you can see, it's a little bit easier to find our t value than it was to find our z value. So go on and do your questions now.